So, and I can go straight to introduction. Before I introduce Colin, just a reminder that next week we have a talk from Mayan Zhu from Nanjing Institute of Geology and Paleontology. And so likely we will do it at different time. I don't remember what time we done it last time, maybe 4 o'clock California time, but just pay attention to the time when we send it. And so with this, it's a great pleasure to introduce Colin Goldblatt. Colin did his undergraduate and PhD in University of East Anglia, in UK, where he already got into Precambrian and did modeling on Great Oxidation event, arguing for once Great Oxidation event happen, it will not happen again. And he moved after it for postdoc to NASA Ames, and in our postdoc at University of Washington, I guess with Kathleen, probably at that time. And after it, since 2011, he was at the University of Victoria, British Columbia, from where he's talking now. And it sounds like he kept coming back to his favorite topic and revisiting Great Oxidation events. So with this, I pass it to Colin.
Okay, thank you, Andre, for that very kind introduction. So I'm indeed going to talk about the things that I failed to do in my PhD, but we've now managed to do here in my group. And some of that is with the work of one of my former students, now graduated Julia Horn, who is supposed to be in the meeting today, but well, it's early in the morning here. So if I can get my slides to change, I want to start by giving our territorial acknowledgement here is that we acknowledge and respect the Algonquin, the Songhees and Esquimalt peoples on whose territory the university stands, and the Algonquin and Wasanich people whose historical relationship with the land and the waters here continues to this day. And for those of you who haven't been up to the University of Victoria, I recommend you visit. In this room, you can see me, you can see Paul, also Blake Dyer, Anne-Sophie Aim, John Husson, people that many of you will know are here at UVic. And it's just a little hop across the border if you need to evacuate from the United States. So this is what I'll talk about today. I'm going to give a little introduction, just a little general introduction, and then talk about a couple of simple models. And one of those is the model I developed in my PhD, and then another is just a little toy model of Snowball Earth. And then I'll go and put them together into what happens if you try to have a great oxidation and Snowball Earth glaciations at the same time. And that was what I couldn't get to work in my PhD, but I'm very proud to be able to show you now. So, our introduction. This is a sketch of the evolution of Earth's atmosphere. I wrote it down one day. I sketched it. This is a cartoon. I will not claim that I was sober when I sketched it, because sketching something across 12 orders of 12 orders of magnitude in dynamical range required a little help. But this is the atmosphere. The main features are that ozone rose to some extent when oxygen-edic photosynthesis evolved. And then we had our great oxidation at 2.5 billion years ago, which took oxygen from less than a part per million to maybe order percent levels with the formation of the ozone layer. Other features that I've drawn here is nitrogen. We have no idea what the history of nitrogen is, other than it may well have changed. Carbon dioxide, we think, may well have decreased during Earth's history. I've drawn that in red here. And water follows the surface temperature of the Earth. So big positive excursions in water inventories would be warm events, impacts perhaps early in Earth history, and negative excursions is Snowball Earth, which Paul has mentioned may actually exist. The only thing that I believe now is wrong on this sketch is the methane inventory. I drew what was fashionable at the time, and I now think what I drew here was complete garbage. So let's talk about ice cover a little bit. This is a figure from Paul, which shows the glacial history of Earth. What I would like you to see in this is that right now we have regional glaciation. That has been the style in the Phanerozoic. But during the Precambrian, we had occasional snowball Earth glaciations. And when there was one snowball Earth glaciation, there may have been more than one snowball Earth or more than one other glaciations. So they're rare, but they come in packs. Now, I converted my talk from a PowerPoint to a PDF to make it easier to transition between the slides on Zoom. This unfortunately turned some of my figures on their side. But I think everyone knows this anyway. We have a few different stable states of climate on Earth. We have a small and large ice cap instability, which means that we will go from our present state now to unglaciated. If we become more glaciated, we will switch to all glaciated. So there are those non-linearities, those bifurcations in the climate system. And I'll need you to just keep this in the back of your head as we go through. And this is the broad timeline of a snowball Earth. We need to get into the snowball Earth somehow. We need to cool the Earth. One option could be to turn down the thermostat on the carbonate silicate weathering cycle. Other people have proposed turning down methane. I don't believe that is plausible. I will talk about that later. That triggers that first instability. Then we have our long snowball Earth glaciation, during which we build up enough carbon dioxide to get us out. That would happen too quickly if we had no sink of carbon dioxide during the glacial. That's a problem we do in my second year class. When we do deglaciate, we've got a lot of CO2 in the atmosphere, which we can't get rid of instantaneously. So we probably go into a very hot aftermath and then deposit cap carbonates, then have enhanced silicate weathering to cool us off. I think it's a story that many of the people in this room will know. For those of you who've not seen it before, welcome. And here's a little figure stolen from someone's paper a few years ago, from a Gunsley paper, looking at how the Great Oxidation happens at the same time as those Palaeoproterozoic Great Oxidations. And we have, in the portion of the figure at the top in blue, where those glaciations are. And at the bottom, we have some of the evidence for oxygen. So it looks like oxygen rises after the glaciations. During the glaciation, we lose the high oxygen again, and then we repeat that cycle a few times. So we've got this intricate linking of snowball Earth and the oxidation. And in the end of this talk, I want to speak to that part of the record with a model. And I'm going to build up the tools that we need to do that through the talk. Okay, so quick summary of my introduction. The Great Oxidation was a rapid increase of oxygen level by a few orders of magnitude, and it was substantially delayed from the origin of oxygenic photosynthesis. The snowball Earth involves two feedback processes, the ice albedo feedback and the carbonate silicate weathering feedback. The former we think of typically as a destabilizing feedback, and the latter we think typically of as a stabilizing feedback. And the Great Oxidation was coincident with those Palaeoproterozoic snowballs, and oxygen likely oscillated during those events. Now, I'm going to talk to you about a simple model of oxygen. And this is really part of the warm-up of the talk. And this is, in fact, work I did for my PhD with a few updates. So I'm going to talk you through that model and some of the implications, especially how that model does permit for oxygen to go up and down. So our model will include oxygenic photosynthesis, decomposition of organic carbon, either by respiration or methane production. We use those two end member metabolisms depending on oxygen level. We have hydrogen escape, and then we have atmospheric oxidation of methane with a parameterized rate based on photochemical models. The original models from 2006 and 2007, we've got an update on that coming out in a Phil Trans paper this year. So here's the model, and I don't think in this talk we should get into exactly what each term in the equations mean, but suffice to say I have one ODE for methane level, I have one ODE for oxygen level, and I have an ODE for organic carbon burial. We're actually going to set that to steady state for the purposes of this talk. One of the most important terms, which is at the bottom right here, is our oxidation of methane, and our parameterization of that, our revised parameterization of that, which we give in this Phil Trans paper, also in GQ paper from last year, is at the bottom. And that just cleans up that parameterization. If anyone is using this model, use what we have here, not the squalid fifth order polynomial that seemed an acceptable idea to me when I was a naive graduate student. Anything else to say about this? We have production of oxygen, production of methane in stoichiometric balance depending on oxygen level. We have hydrogen escape from methane. We have methane oxidation in the atmosphere. So here are the main processes. We have oxygen production by oxygenic photosynthesis. Without oxygen, that organic matter is decomposed via fermentation followed by methanogenesis to make oxygen and methane in a stoichiometric balance. So we see the oxygen source in the original equation, we see the methane source in that second equation. So the biosphere net produces oxygen and methane. That cycle must be closed in the atmosphere. The methane is oxidized in the atmosphere, so we have a closed geochemical cycle. I think everyone in this room knows that it's important to think about closed geochemical cycles. In a model, it is a mathematical requirement to close our geochemical cycles in order to conserve mass. So that is a critical thing of how we've got to think about the Archean atmosphere. If we're producing methane, we're closing that cycle by atmospheric oxidation. That's a photooxidation process. Let's take a little aside into ozone formation. Here are the Chapman cycle here, which says that oxygen will start to be formed as soon as we have appreciable oxygen in the atmosphere. The threshold is that we need to absorb a sufficient amount of photons at 240 nanometers or less in order to split that oxygen to make our oxygen and thus make ozone. So to make the ozone layer, we require some threshold thickness of oxygen column depth. We don't have enough oxygen, we don't make ozone. And it turns out that that column depth is equivalent to about a part per million in the atmosphere. So what happens then? Well, this is a figure from a paper from Jim Casting from many decades ago. And if it's a little small to read on Zoom, I'll talk you through it. We've got profiles for the ozone column, for the ozone density as a function of altitude at different oxygen levels. So on the left-hand side of the plot, there's 10 to the minus 5 of oxygen, 10 to the minus 4, 3, 2, minus 1, and the present atmospheric level of oxygen. So what we see is as we start to form oxygen, where we have 10 to the minus 5 PAL of when we start from ozone at 10 to the minus 5 PaL of O2, we have a little bit of an ozone layer. That ozone layer thickens as we get to 10 to the minus 3 PaL of O2, but then it moves upward rather than thickening. And the reason it moves upwards is that we can get to oxygen, dioxygen being optically thick in the UV, higher up in the atmosphere when our concentration of oxygen is higher. So we're forming as much ozone as we can because we're absorbing all of those UV photons. And we get to that threshold where we're absorbing all of those photons at about 10 to the minus 3 of dioxygen. So after that, we just form the ozone layer higher rather than making it thicker. So why is this important to our methane problem? Well, atmospheric chemistry is largely done by hydroxyl radical. I think it was Paul Crutzen who described this as the detergent of the atmosphere. And we get our hydroxyl radical from photolysis of water vapor. Water vapor is largely in the troposphere. The stratosphere is too cold to get much water vapor in. So once we have an ozone layer, we protect the troposphere from UV radiation. We've got a nice sunscreen on. But in the Archean, we didn't have that sunscreen. We'd get a lot of UV to the troposphere, and we would produce a lot of OH. And that means that our reactions are going to happen very quickly. So we put all that together in the model. And what we find is that we have two stable states of oxygen. And that occurs because of this nonlinearity in atmospheric chemistry. In the Archean, oxygen and methane are destroyed slowly. Sorry, that's entirely the wrong way round. In the Archean, oxygen and ozone are destroyed quickly because we've got a lot of UV flux, a lot of hydroxyl radicals. That hydroxyl radical will attack the methane, destroy oxygen and ozone together quickly. When we go through the Great Oxidation, we slow down that chemistry, and slowing down the chemistry means that we can accumulate oxygen. And I've plotted the stable states here as solid or dashed lines with a little dotted line for unstable steady states. And I've plotted it as a function on the top plot of our net reductant input to the surface systems. This is really whatever we're driving the model for. It could be a mantle flux, for example. The grey shaded areas are some estimates from Dick Holland of what the mantle ion flux was. The bottom panel, we've showed it as a function of net primary productivity from oxygenic photosynthesis. So with low productivity, we will always have low oxygen levels, less than a ppm. But once we increase primary productivity beyond a threshold, we can move to high oxygen levels. And we can find the values of reductant input or net primary productivity where two oxygen levels are possible at the same input flux. And in fact, we can do some more algebra and come up with a term, with primary productivity minus reductant input and a few other terms to give a single term showing the oxygen level. Something that's important here. If I turn up primary productivity, I'll go to a system where only high oxygen is stable. If I turn down primary productivity, I will go back to a system where only low oxygen is stable. So a natural consequence of this model is that the Great Oxidation is easily reversible. It just requires the willingness to turn the crank on primary productivity levels. I think this is a widely misunderstood aspect of this paper. My excuse will be I was a graduate student when I wrote it, so you don't always know the right points to hammer home. Okay. Just as a little tip to some of our new results, we also showed that this is dependent on temperature. So I've got a couple of papers with Daniel Garduno-Ruiz, who's a amazing graduate student of mine, is going to be graduating this year. If anyone wants to pick up a good atmospheric chemist, talk to Daniel. And we show that the amount of oxygen that we'll get in the atmosphere, the thickness of the ozone, the amount of methane, all depends on the temperature. And in fact, it is possible to make oxygen oscillate simply by making temperature oscillate if you line everything up just right in the model. That's not the explanation I'm going to give today, but it is one of the possible explanations for these oscillations. Okay, section summary. We can have high oxygen or low oxygen. We can't have middle oxygen, that's not allowed. And we can switch between the two of them depending on how we pull the levers on our model. And I think that's all. That's the really important thing from this simple model. Now, I want to give a couple of slides from a very simple model, a very simple coupled carbon cycle model talking about Snowball Earth. And this is something that I've been doing very recently and hopefully will write a paper on this year if I can relieve myself from the administrative purgatory which comes from actually being a professor rather than a retired professor. And I'm seeing Paul smirk there. So we've got two ODEs, one for temperature, one for CO2 level. Temperature, I've got a simple parameterization of that. CO2 level, I've got weathering, ultimately draws down CO2 volcanism that puts it into the atmosphere. This is a simple model that many people may have built. What's really important in the model, sea ice is bright, ocean is dark, so we have a nonlinearity. This is a cubic nonlinearity in the model. And then this is just an example from one of my homeworks from my fourth year class, is we can either get hot or cold climate. These are different CO2 levels. You know, and I have some where I can get hot or cold, some where I can get hot, some I can get cold because of this instability. Now, I'm going to show two plots like this. And this is when I've tuned the model one way. So on the left-hand side, we have the, well, my fonts are outrageously small, such that I would have docked marks from the students for these font sizes. On the top, I've got 3 columns for different rates of volcanism to force the model a bit differently. The top is with higher volcanism, the bottom is with lowest volcanism, then the other one is the middle. The top plot shows that I've got a lot of volcanism, I end up with hot climate. The bottom one, I have not much volcanism, I end up with cold climate, snowball Earth climate. And the middle one, I've tuned it just right, that I can get either hot climate, ice-free, or cold climate with snowball Earth. So that is the classic bistability. Now, I'm going to tune my model a slightly different way. The top I get ice-free, the bottom I get snowball Earth. The middle, I get a limit cycle. I get self-sustaining oscillations between snowball Earth and ice-free conditions, just with a little bit of tuning of the model, because as a modeler I get to play God. So it's pretty easy then to see why snowball Earth could come in packs, because if I tune my carbon cycle model just right, when I deglaciate, my weathering is sufficient to pull my the surface temperature back down below the threshold where I would go back into glaciation. So I go in and out of glaciation in a continual cycle. So with this model, we can have stable ice-free conditions, stable snowball Earth conditions. We could have bistable conditions where we could either have ice-free or snowball, or we could have self-sustaining oscillations between ice-free and snowball conditions. So that set us up for the main course of the talk here, which is we're going to use a new coupled biogeochemical model that my student Julia Horn, my former student Julia Horn, Julia graduated a few years ago, well, 1 year ago, I think, after an epic and exceptionally productive PhD building this model. And we can do everything because this model has the kitchen sink in it. So here's Julia. It's not 8 a.m. in the morning, so Julia is entirely present and correct on her graduation day. And there's a link to our EONS paper. We have coupled carbon, oxygen, nitrogen, and phosphorus cycles, coupling the atmosphere, many ocean reservoirs, and sediment and continental reservoirs there. There are 96 model reservoirs connected by 257 fluxes. If I think the threshold was 260, at which point Julia would have killed me. Okay, quick schematic of the model. Atmosphere, surface ocean, deep ocean, few sediment boxes, ocean crust, a very simple mantle, continent, and exchanges between all of those over time. This will be too small to read, but it will tell you which species we represent in each box. And then I showed you at the beginning of the talk my cartoon of atmospheric evolution that I simply drew one day. This is the nominal run of our EONS model, showing atmospheric evolution over those same 12 orders of magnitude, predicted by a model. And our modeling philosophy here is to apply minimal evolutionary forcing to the model. So during this model run, we apply 4 evolutionary forcings. At the left of the model, marked with a P, is the evolution of oxygenic photosynthesis. Marked with an F in the Neoproterozoic is the evolution of fungi and enhancement of weathering due to fungi. B, enhancement of burial by bigness of organisms for more burial. And then L, land plants. And we turn each of those on slowly over 100 million years roughly for numerical stability in the model. And then we also force the model by a very slow linear decline in a flux of reductant from the mantle. And that's it. Everything else in this model is internal dynamics of the model. It has to go from essentially an abiotic Earth. We start it with the origin of with the origin of the biosphere, of anoxygenic photosynthesis. We don't show the first little bit of the model, the first 10,000 years or so, because that's quite messy. But then everything else is the evolution of the biosphere here. So we see a very nicely timed great oxidation. We see that methane, that's our bright green line, decreases during the Archean, but then increases at the great oxidation. And the reason for that is, in fact, completely obvious, which is the great oxidation built the ozone layer, that great sunscreen of the Earth. So we slow down the reaction of methane and oxygen in the atmosphere. You slow down a reaction, well, that allows oxygen to increase. It also allows methane levels to increase. So I'm definitely in the camp of a higher methane Proterozoic. our models indicate a slightly lower methane Archean normally, but we could, if we twiddled, we could maybe get that a little bit higher. The other thing is in the Proterozoic, we tend to have somewhat higher productivity, and high productivity is really good for methane. To get methane levels low, we really need to oxidize the deep ocean, which we don't do until the Phanerozoic. Okay, anything else to talk about in this little screen now? Well, of course, like everyone else who's worked on the faint young sun problem, we tried to solve the faint young sun with ammonia, because we all know that ammonia is the best greenhouse gas. That was what Carl Sagan proposed. We could manage to maybe get it to 1 part per billion. Sometimes, no, we couldn't get any substantive greenhouse effect out of ammonia, but we tried, as everyone else who's worked on this problem tried. So, as I mentioned, our modeling philosophy is minimal time-dependent forcings. And I'm going to contrast that to something like geocarb, which has very intricate time-dependent forcings, so which allows that model to get pretty much whatever history you want the model to get, because you give it the forcing that will give you the answer that you want. But we don't do that because we want to make our life more difficult. That is, say that our model has to be able to naturally reproduce the Earth's history. That's really difficult as a modeling task, it turns out. The other thing I'll say is that we realize that Earth never gets to steady state because we have very slow reservoirs, like organic carbon in the continent, which might have a lifetime of 500 million years. So to get the continent genuinely into steady state will never actually happen. The atmosphere will be in steady state with respect to the continents. But the continents themselves, and therefore the whole system, or the mantle and therefore the whole system, is never in steady state. So when we make assumptions like, let's assume the modern is in steady state and tune our model to a modern steady state, that doesn't work. Okay, there's a lot of words because the previous version of this talk I was giving to non-native English speakers. So I'll go through them quickly. So the motivation question we're going to look at is the Great Oxidation and Palaeoproterozoic glaciations. I've never believed that methane could cause the glaciations because it's not a very good greenhouse gas. I've always thought it will go up at the Great Oxidation. We're going to try to hammer some more nails into that coffin today. Modeling of that, the glaciations, is a little challenging, but I think we've got some nice model results for you. Okay, couple of modifications to our standard EONS model. We put a nice albedo feedback in. We put a super greenhouse feedback in for the deglaciation. And we've got a paper on that, which is in review. We need to do revisions. Okay. So I'm going to show you results from 2 experiments here. One is with a very slow forcing, equivalent to our nominal case, and that's going to give us 1 glaciation and a great oxidation. I'm also going to show you a set of runs where I have a 500 million year period oscillation in the carbon cycle, and then I'll get a suite of glaciations within that 500 million year oscillation. That is our multiple glaciations, which may well reproduce the record. So I have some busy figures here, and we're going to have a few of these figures, and I hope people can read at least the bigger words on these. On the left-hand side, I have about 500 million years of Earth history across the Archean Proterozoic transition. On the right-hand side, I have an enlargement of a shaded area, which unfortunately has not shown up on my screen here. But suffice to say that I did shade an area around the obvious wiggles in the middle on the left-hand side, which are the glaciations and the Great Oxidation. So the right-hand side is an enlargement, and that's about 20 million years of time. So let's start at the top, and I'm just going to work down, talking you through some of the features of the Great Oxidation triggered by snowball Earth. So on the top, we have surface temperature. It is stable. There is an imperceptible decline in surface temperature until we hit a threshold. I'm using my mouse as a pointer here. Are people able to see that or not? Paul, you can. Okay, thank you. So we've got a temperature. We decline into snowball glaciation. We recover from glaciation, pop out into a super greenhouse, restore stable climate. On the enlargement, we see that writ large. We have snowball Earth, exit, very hot climate, restore temperate climate. Now let's look at the atmospheric composition. We've got oxygen in yellow, carbon dioxide in green, methane in blue. So let's look on the enlargement. We have low oxygen at the beginning. That's about 10 to the minus 7 mixing ratio of oxygen. When we get into the Great Oxidation, primary productivity crashes. Therefore, we have very low oxygen through the glaciation. At the deglaciation, oxygen increases rapidly, and we stabilize to about 10 to the minus 3 mixing ratio of oxygen. We look in green at carbon dioxide, that is at moderate levels. It actually drops just as we go into the glaciation. I will tell you why in a moment, but then it grows during the glaciation, peaks just at deglaciation. I will tell you why on the next slide, and then decreases afterwards, restoring stable climate. Methane we'll see in blue increases somewhat during the glaciation, and that's because there's not a lot of oxygen around to get rid of that methane. Now, the next slide we have, so the next panel we have with the blue, green, and grey lines is the radiative forcing from those greenhouse gases. So what we can see is that the carbon dioxide radiative forcing dominates. In this context, it's the much stronger greenhouse gas than methane. We only think of methane as a strong greenhouse gas today because we only have 1 part per million in the atmosphere. So we add a part per million methane, we double the concentration. We add a part per million carbon dioxide, we increase the concentration by 1 part in 400, and radiative forcing depends on the logarithm of concentration. So we always need to remember that. Methane is a weak greenhouse gas in a paleoclimate context because it is inherently less strong than CO2. Methane appears stronger in the modern context only because its concentration is so small, so it's so easy to double the concentration. So we do not see a decrease in methane going into the glaciation. We do not see a decrease in radiative forcing from methane going into the glaciation. CO2 decrease causes the snowball Earth. So look at our ocean chemistry. That's the bright blue line. We've got a couple of wiggles as we go in. I'm going to come back to those on the next slide. Our ocean becomes a little bit more acid during the ocean. The slide below that green peak shows our cap carbonate deposition. That's our total carbonate deposition. Our deglaciation precipitates about 270 meters of cap carbonate. During the glaciation, we do precipitate carbon into ocean crust. Ocean crust carbonatization does still occur during the glaciation, and we find that is essential to getting the length of the glaciation to be correct. And we assume that there is some exchange between the atmosphere and ocean. We don't need a lot of ocean water. I think an area about the size of Vancouver Island is probably sufficient. And there is liquid water at the bottom of the ocean, so we can alter ocean crust. Light blue line is weathering. Of course, it decreases during the glaciation. It increases on deglaciation when it gets very hot. So that big pulse of nutrients is quite important for oxygen because it really drives a big increase in productivity, also in carbon burial here, shown in the dark blue line. The bottom, I show my forcing, and I've just got this very slow decrease in mantle forcing, which drives the system very slowly through Earth's history in our model, and that's that purple line. Okay, I'm going to look a little more at the controls on the carbon cycle here. One interesting feature that we note in our models is that we have a solubility feedback. Carbon dioxide is, of course, more soluble in cold water. So as we go into the glacial, as we start to glaciate, as we'll get into the regional glaciation first, and it takes us a few years to get into global glaciation, we suck CO2 out of the atmosphere into the ocean because the ocean is getting colder. So that is in fact a positive feedback which helps us get into snowball Earth. In these models, we can, if we don't have that, we actually avoid snowball Earth in many of our model runs. So then when we deglaciate, we put a pulse of CO2 back into the atmosphere as we warm the atmosphere. So that really helps us get to very hot conditions on deglaciation. What else do I want to look at? So we can see part of that if we look at the penultimate graph at the bottom, that's our CO2 levels. We've had that very slow decline coming in, but as we start to cool the Earth in regional glaciation, then we get a rapid drawdown of CO2 as the ocean gets colder, and that pushes us into snowball Earth. Now let's look at the controls on oxygen. So let's start. Our phosphorus flux, that's dependent on weathering. So if temperature is our top panel here, next panel here is phosphorus fluxes from weathering in light blue and from calcium-bound phosphorus burial, that's calcium carbonate-bound phosphorus in the dark blue, which is a removal. So we get less phosphorus coming in when we're in glaciation, big spike in phosphorus at deglaciation. So that's really going to drive primary productivity. So that's that third line there is our primary productivity. Is in this model, we model primary productivity as nutrient limited. We have both nitrogen and phosphorus represented in the ocean. Productivity requires both, but we can fix nitrogen. So the ultimate limitation on productivity is phosphorus availability because that comes from the land. So when we shut off phosphorus input, we're going to really crank down that productivity. And we do that by a few orders of magnitude at glaciation. And these plots, of course, are all on a log scale. So yes, we've still got some phosphorus input because weathering isn't zero. It's just very, very small. So primary productivity follows glaciation. And methane fluxes, of course, that's the fourth plot, follow primary productivity. And then our oxygen levels in the penultimate plot, we've got oxygen at about a part per million before, decreasing to a part per million during the glaciation, And then we see over a period of the right here, we've got about 10,000 years zoomed in on the right bit of the plot. We get oxygen increasing over about 10,000 years on deglaciation, and then the Great Oxidation. So there is a little period of about 10,000 years in our model where we've got out of glaciation, but we haven't had the Great Oxidation because we've got to have have oxygen, give it enough time to accumulate in the model. That takes 10,000 years. That may have an implication for geological data, is that if we see something immediately on deglaciation, that may be anoxic still, but directly after we would predict it would be oxic. Very bottom plot, methane gives us a decent amount of radiative forcing during the glaciation. That means we need less CO2 to get out of the glaciation. So methane is helping us deglaciate. It is not causing the glaciation. Okay. I think I've talked about that enough. There's a summary though. Now here's the money plot. It's the multiple glaciations. So what I've done at the bottom, we're going to start at the bottom on this one, is put a very long wavelength, 500 million year timescale wavelength perturbation to the carbon cycle. We had more volcanic input in the Neo-Archean, less in the Palaeoproterozoic. 500 million years we picked because it's the timescale of a Wilson cycle. So we think of this as very long timescale geological forcing. Let's have supercontinent breakup or assembly. We've got some evidence in the Neo-Archean that we probably had quite reducing conditions there, which would have required higher flux of reductant. So let's put that in and let that drop off in the Palaeoproterozoic. And what we see looking directly above is that we get a series of glaciations, and this perturbation of the carbon cycle has changed some of the parameters in our carbon model. It's done the equivalent of changed the tuning that I did in the introduction to take us to a regime where instead of getting stable glacial or stable non-glacial, it's perturbed the model such that we're in a position where it naturally oscillates between glacial and non-glacial conditions. So we see at the top oscillations in and out of timing, in and out of snowball Earth glaciations. The timing of these does not perfectly match the geologic record. It never will. This is a model. And a model forced with very simple forcings. The point is we get a series of glaciations. And with our series of glaciations, if we look at the yellow line in the second row, we see oxygen starts to increase before the first, but it crashes during glaciation. The Great Oxidation. The next glaciation crashes oxygen. Oxygen rises in between again. Oxygen crashes. Oxygen rises at the end and stays high. So we see, using our glacial interglacial mechanisms with the carbon cycle, we can drive oscillations in glaciation, drive self-sustaining oscillations. Once we do that, that will force the oxygen system into oscillations between low oxygen and high oxygen. And I think this may be sufficient to explain what we see in the geologic record of evidence for oxygen between glaciations, evidence for low oxygen around those glaciations. And then we see the same features in all of our other parameters that I went through for a single glaciation. So that is my summary from this section. We can use our dynamics of the carbon cycle to give us cycles between snowball and non-snowball conditions, and that will force our oxygen levels. So I will give you my conclusion here is that our EONS model is naturally able to simulate multiple glaciations and the interactions with oxygen, including these elusive oxygen oscillations through our cycle of snowball Earth glaciations. Thank you all for your attention this morning, so early in the morning for those of us on the West Coast. And I look forward to all of your questions.
Thank you, Colin. And so we can now switch to questions. So people can raise their hands or sort of type in the chat and I will read, preferably the first one. So we start as usual with Greg. Greg, go ahead.
Thanks, Andrew. That was awesome. Now, as I understand it, your fundamental assumption is that there was no life on land, and that the carbon cycle on land had nothing to do with it. It's all in the ocean and the atmosphere, and it's all driven by volcanic pulses, right?
I somewhat agree with some of your assertions there. Our model is really driven by the ocean carbon cycle. We turn on the land carbon cycle later in the model. Is it driven by volcanic pulses? No, we are not pulsing volcanism here.
Okay.
In our nominal run, our volcanism is the most boring thing in the world. It just decreases linearly by a factor of a few over Earth's history.
I see.
And then in our final run, we put one slow variation modeled as a sinusoid with a 500 million year wavelength. So it's dynamics of the model which gives these features.
Very good. And the weathering model is entirely temperature-based abiotic weathering without any input from any biota that might have been on land, right?
Yeah, so weathering's parameterized based on temperature and CO2 levels. We turn on much later in the model in the in the near Proterozoic some land-based weathering. We don't have biotic enhancement here.
I'll have to send you some of my papers, but I need to get off because you've got lots of questions here. But thanks so much. That was great.
Thank you.
Thanks. So Jinyun Liu, go ahead.
Yes, thanks, Colin. This is a fabulous talk. I have so many questions. I'll just ask one right now because a lot of people are waiting. My question is concerning because you update your 06 model, and I wonder what's the changes in the massing flux from your 06 model to the one you're using. I noticed that the massing concentration was about the same, 10 to the minus 4 bar.
Yeah.
So any updates on the flux number?
No, I would really call it housekeeping updates on the model. Is there are some parameterizations which I look back at the way I did when I was young and foolish and didn't like, and we cleaned them up. So it's nothing is really changed in the results, but the way the model is parameterized is a little cleaner. It's a we did a remarkably good job back then. This is, I've got, as I'm sure everyone in the room does, I've got papers that I look back on and I'm like, oh, that was fine. And I look back on this one and I think we did a remarkably good job at getting the main features right. And we've tidied it up with newer photochemical runs and with a mathematically better behaved parameterization for methane oxidation, but no big deal changes. The paper, the Filtrans paper that's going to be out quite soon, we use the model to talk about a quite curious result, which is the earlier the origin of oxygenic photosynthesis is, the longer the delay until the great oxidation. And that's because of throttling back accumulate. Oh dear, I didn't practice this, but it's about throttling back the carbon cycle and productivity and about the phosphorus cycle and about how you build up the organic carbon reservoir. But that was what we were writing that paper for, to talk about the time delay And we get this really counterintuitive result of a longer time delay the earlier the origin of oxygenic photosynthesis was. Sorry, that's aside from your question.
Okay, so maybe Paul next.
Yeah, thanks, Colin. Highly stimulating. One thing that might be interesting to add would be temperature-dependent respiration. Respiration is more temperature-dependent than productivity. So, for example, in snowball aftermath, when it gets very hot, respiration rates will be extremely high, and as a result, carbon burial will be reduced, and so will oxygen production. Conversely, if you have a glaciation that is not a snowball, so that organic productivity continues, lower temperatures will reduce respiration and therefore lead to higher organic burial and increase in oxygen. So it might be an interesting and perhaps not too difficult thing to add would be the temperature dependence of respiration.
No, that's a nice point. We will try that at some point. Thanks, Paul.
Okay, Eva, go ahead.
Thanks for your talk. It's really cool stuff. So I was wondering what your model would say about oxygen whiffs in the Archean. Are they possible, I guess, or maybe the other way to ask this question, how many, I guess, how large sort of amplitude for high frequency fluctuations in oxygen does your model allow? Yes.
So the way I think about oxygen whiffs is that there will be in the Archean, there will be high oxygen locally in shallow marine environments, or for the people who like it on land, in shallow lake environments where we're actually getting our oxygen production. So we do have a representation of the surface ocean, and particularly we treat how much of that productivity happens in coastal area. So we could draw out of the model an estimate for dissolved oxygen levels in the surface ocean. And I think that would show them getting reasonably high. In terms of whiffs whiffs in the atmosphere, I think it's very we will get plumes of oxygen, but then they will mix into the atmosphere, quite quickly, or it'll be very homogeneous. So I don't know in an atmospheric context what we really mean by a whiff. I think we'll certainly get high oxygen in the water column in shallow water environments. We're not going to represent a plume of oxygen in the atmosphere because our atmosphere is well mixed. But if you tell me exactly what you want your whiff to be like, I can see what we can make in our model.
Yeah, I guess I was thinking of the earlier part of your talk, and I guess what you did in your PhD with a sort of bistable atmosphere. So if you, let's say you have a little plume of oxygen, so I guess in the Archean it would be probably more difficult to reach that sort of second stable state if you have still a lot of sort of reductant around. So how long could that little plume last before it's sort of forced back down to the...
Yeah, thanks, Eva. I think I'll tell you what I understand from my models, which is that we predict stable oxygen levels in the Archean of order 1 part per million oxygen. So if we were in the model, we could probably do a transient run of our model where we gave the model a kick of organic carbon burial. And let's just give it a little pulse of that for 10,000 years. Let's give it an event scale perturbation. That would give us an event where we started to accumulate oxygen up to maybe even great oxidation levels, but it would go down again if we took away that pulse. So, if you got oxygen up, you could get oxygen to like the 10 to the -3 level, in a transient run, which isn't stable. So if we want a whiff, it's just about willingness to do it on an event time scale, I think.
Okay.
So we can occupy the unstable region transiently, just not for tens of millions of years.
Okay, so basically for the duration of the trigger.
Yes.
Yeah. Okay, cool. Thanks.
Yeah.
Okay, Jinyun, Liu again.
Yeah, Jingzhen, by the way. Yeah, sorry, to me again. I have two follow-up questions on the CO2 and oxygen. So I noticed in one of your slides, the oxygen level during the glaciation was quite low, 10 to the minus 10 PAL. I just wonder, that can be the cases in the Paleoproterozoic snowball, but probably doesn't work for the Neoproterozoic one because we don't see the return of the sulfur myth in the Neoproterozoic one. So what's your thoughts on that?
We have not chosen to model the Neoproterozoic at this time. That will be a great project with this model for a future student. If anyone has got a really a student who really understands geochemistry and geology and is also good with maths and computers, then send me that student and we'll do the Neoproterozoic. Paul's just put his hand up, so maybe Paul's going to be that student. Paul, you're going to have to learn some maths.
Well, chloralkanite flushing does provide a way of burying organic matter and producing oxygen during a snowball.
Yeah, so I think in our model, it depends on what's going to give primary productivity to drive the oxygen levels. So wherever you can get your primary productivity, that's going to help keep oxygen levels up. I can now see Ben Johnson's hand up, and I think Ben is just going to come to my rescue here on this question. Are you going to rescue me, Ben?
No.
Oh, you're going to throw your old advisor under the bus. Okay.
Well, I had a question for you.
Yeah. Thanks, Ben.
Yeah, no rescue, only questions. Is there, I missed the very first part of your talk, so sorry if you talked about this already. For the organic matter that gets buried, so that buries carbon and nitrogen and phosphorus.
Yeah.
Is that in a fixed ratio, or have you tried like allowing that to go up and down at all? Do you think that would change any of the like dynamics if that ratio changed a little bit?
Yeah, we certainly tried that at one point, and I think it broke everything and we couldn't fix it in the model.
Okay. Yeah.
So I'm pretty sure this version of the model, we're using a fixed Redfield ratio throughout. We've never managed to really get that ratio changing and the model be stable to doing that. It requires a little bit more cleverness than we've managed, I think. Have you managed that in any of your models, Ben?
No, I've never tried it, so
yeah,
it makes sense that it would be hard. I think.
It's a real pain.
Yeah. Cool. Thanks, Colin.
Yeah. Thanks, Ben.
Yeah, I'll follow up on that. On the CO2 side, I would like to know. I wonder, how did you parameterize your CO2 in the model? Because I noticed it's in the Archean values remain relatively low, like 1% ish, and you have a feedback that links the CO2 to your methane, right? And also, I asked this because I think there are recently 2 independent estimates on the Archean CO2 from David Catling's group and Jim Casting's group on the micrometeor oxidation state. I think the lower limit is about like 0.2 bars. Yeah, I just wonder like how it's related to that.
Yeah. So if this has happened in this seminar series, and I've missed it, I've not been able to get to them this term, I apologize until now. It might be fun to get Kevin Zarnley in to talk about those micrometeorites because he has some opinions on them. If you could get him to talk at 8 o'clock in the morning, you'd get some entertainment. That's all I'll say on that. So our CO2, the big driver of CO2 is carbonate silicate weathering. So we have CO2 represented in the atmosphere. That CO2 communicates with the ocean. It exchanges naturally with the ocean. In the ocean, with a DIC reservoir. In the ocean, we also represent an explicit alkalinity reservoir. And then we have alkalinity sources from weathering of carbonates and silicate rocks, and alkalinity removal through carbonate deposition, and we also represent reverse weathering. So we've got a full set of processes which affect an inorganic carbon cycle. What affects the CO2 level? There's a couple of things that do that. One is how we parameterize temperature dependent on CO2. So we can get a stable temperature, in Neo-Archean with about 30,000 ppm of CO2 following GCM results. Then the saturation state at which carbonate deposition occurs is really important. And the parameterization of weathering as a function of temperature and CO2 is really important, as is a few other parameterizations. So I think one of the things to always know about these models is they're all tuned. And we have to tune the model to a certain set of a priori assumptions about how the world works. So one of our assumptions was that we had, a late Archean that had temperatures somewhat like today's temperatures. And following the GCM results, that was around 30,000 ppm of CO2. So that's why it's lower than the results that you're calling for, because the way we tuned the combination of all those parameters was for that assumption. So one could look at different assumptions and then look at the consequences of them with a different model tuning, which requires, you need to put your elbow length rubber gloves on and really get into the model and do that if that's something that one wants to try.
A very last follow-up. So in that situation, did you fix the CO2 concentration per your GCM result, or did you balance it in the fluxes?
Yeah.
Going
So
to it?
when we do a lot of GCM work in my group now to look at the climate, and we will fix a GCM. We'll fix a CO2 in the GCM, run the climate model. We'll fix a different CO2, run the climate model, because we can run, 30-year slices of climate models, which is enough to get the atmosphere into equilibrium, but not enough to do any geochemistry. So we just run the GCMs for different CO2 levels. Tell me what you want, I'll run you a GCM.
Got it. Thank you.
Pleasure.
Okay. Colin, great talk. Maybe I ask a couple of questions. So I'm glad you can reproduce this oscillatory nature that for GOE that we kind of expected. But if you take a broader look, sort of you have a transition from low productivity in Archean to high productivity in Palaeoproterozoic. So do you have any connection, like with increase in oxygen, that would affect flux of nutrients to drive this sort of higher productivity in Proterozoic compared to low in Archean? That's one question. And second one, sort of what triggered getting into this oscillatory state, and what triggered kind of getting out of it?
Okay. So Anve, you've saved the most difficult questions until last. So the productivity really depends on the phosphorus cycle in the model. And there's a few mechanisms of removal of phosphorus, including carbonate-bound phosphorus removal and phosphorus removal in organic carbon. Now,
Higher information.
iron, I think we've represented that as well. I really need Julia here to remember every parameterization in the model. This is what I think is most important in the Archean, is that we start the model with no buried organic carbon, because at the origin of life, there's no buried organic carbon. And we've got to build up that reservoir over time. And once we've built that reservoir up, weathering that organic carbon can be a phosphorus source as well. But while we're building it up, it's only a sink of phosphorus. So it keeps drawing that phosphorus down. Same with our carbonate reservoir. We're building up a carbonate reservoir through the Archean. Once we weather that, that puts phosphorus in. But when there's no carbonate really there to weather, we're just building up that reservoir, that pulls down phosphorus too. So this turned out to be a huge problem for us, figuring this out, getting to a nominal run of the model, is because we were just always taking phosphorus out at the beginning of the model. That was one of the things that we learned that we didn't expect to learn. So onto the going in and out of the conditions for cyclic glaciation. In the model, we do it where there's a few different parameterized ways that we can do in the model. It may be as simple as there was a bigger volcanic carbon flux, that volcanic carbon flux decreases. I think it's a bit more complicated than that. I think it relates to the CO2 dependency of chemical weathering. It may also relate to the shape of the ice albedo bifurcation here. So moving the continents around will change that. Changing the equator to pole temperature gradient will change it. I would like to be able to give you really clear answers on that. And when I mentioned a Goldblatt in PhET paper, that's where I really want to get some time to work on that over this summer and give you some really solid answers to that question in the context of a simple model.
Thanks. And just to continue on phosphorus, did anyone, or did you in your model, anyone try to consider, like, with increase in oxygen, that potentially a flux of phosphorus, continental flux, can also increase? Like, for example, you increase oxygen, you oxidize more organic matter, releasing organic phosphorus. You oxidize pyrites, so more acidic meteoric waters, more intense chemical weathering. So in this way, kind of each sort of oxygen level would correspond to different phosphorus flux, and when it's kind of drives a different level of productivity.
Yeah. So we have some of those processes in. We have oxygen-dependent weathering of organic matter in there, so that is going to kick off after the Great Oxidation. We don't have a sulfur cycle in our model, so there isn't the pyrite processes aren't represented there, and it would be lovely to have a sulfur cycle in the model as well, but we've got a lot in there already. So somewhat is my answer.
Okay, thank you. And looks like Paul has another question.
Well, the delta C13 of carbonate shows no overall change over geologic time, which suggests that the relative proportions of organic and carbonate carbon burial have also not changed, which probably is simply a reflection of the fact that the flux of phosphorus and alkalinity hasn't changed because the composition of the continental crust hasn't changed.
Yeah, I don't think that's a question, Paul. I think that's a comment.
Yeah.
Right. And,
it's a constraint.
Yeah. We would love at some point to predict isotopes with the model. That's again going to require another student to work on the model. It's going to just be a big computing task to get that to happen.
Okay, and Greg, you
Yeah, I bugged out earlier because I thought you were constrained to actually leave by 9. But yeah, Paul has stimulated me to comment that yes, that carbon burial in the ocean has been relatively constant, but in paleosols, not so. In fact, there's a great ramping up of productivity right before the snowball Earth, both the first one and the second one, which is evident from a tau analysis of paleosols through the Precambrian. So my view is that the whole thing is actually driven by biotic enhancement of weathering, by major advances in the evolution of life. I have a talk on YouTube about this, and I gave it to the Geological Society of India a couple of weeks ago as well. I'll send you some papers. It's a different way of viewing the system. In my view, since weathering is so important to all of these models, what happens to actually create that phosphorus supply in the soils is the most important thing.
Yeah. So I think given that's not a question, I'm going to turn it round and make it a question for you then. Is what in your view of Earth history, when did let's say fungi, which are going to do a lot of the mining of the soils, when did they evolve in your view?
Oh, well, fungi evolved at about 2.1 at least, because we have this fossil called Dyschagma from the Heckport Paleosol in South Africa. So that was a terrestrial fungus. But before that, even at 3 billion, we have evidence of actinobacteria. Actinobacteria do everything that fungi do and more, but of course they're prokaryotic. They're not eukaryotic. And we have that from these wonderful spindle fossils, which go way back in the Chert record, both mainly in paleosols, as far as I can tell, that have such a broad array of carbon isotopic compositions as if they were heterotrophic. Whereas the other microbes in the same section, single cell analyses, show very consistent trends for methanogens, which were abundant in Archean soils, and for photosynthetic sulfur bacteria, anaerobic producers.
Okay.
Go on.
Well, the great thing about a model like this is we can test hypotheses in there. So you're putting forward a hypothesis, which is, an early origin of land. So if you can give me an estimate of how much land we have, which is also important, we can put in a representation of we can change how we enhance the weathering from land as a function of time. We have a baseline level, which is not explicitly abiotic. But we have a biotic enhancement, but we can change that enhancement signal in a model and get the model output, which tests that, as opposed to, as a, really a theoretician rather than a field geologist. In terms of the interpretation of the record, I'll just have to nominate a champion, and I'll nominate Paul as my champion if there's a fight about what the geologic record represents.
And of course, you probably also know, and Paul does, that I don't think the cap carbonates are marine at all. I think they're calcareous loess. Some of them, like the Noonday Dolomite, is like the Chinese loess plateau, and others are like the Peoria loess of the Midwestern US. These tell us nothing, in my opinion, about what's going on in the ocean. They just tell us that the glaciers were followed by loess, like they were the last time.
The aragonite crystal fans are not loose. And if the cap dolomites are loose, it's going to be hard to explain the carbon isotopes.
It turns out that those crystal fans are probably fungal precipitates.
Boys, you're going to have to discuss this one later.
I know. It's I think it's well, anyway, we have alternatives, and the modeling would be great. This is why I wanted to establish what your parameters were at the very beginning, because I can envisage a very different set of models. And you can too.
And I think I'm going to give that strictly in the modeling sense, is that we represent weathering based on temperature and CO2 levels
Right.
with some parameters, and we can tune that parameter. The flip side is we represent carbonate burial based on the saturation state, and then we need to tune the saturation state at which burial occurs. And we were working on that recently in, I can't remember if it's in the Phil Trans paper or another paper that Julia, myself, and Lee Kump have in prep, where we've been looking at where we look at different innovations in the calcite precipitation through Earth history. So these biologic innovations are really critical. And if the Earth will change when we put in any biological perturbation to the carbon cycle.
Right.
And, we try to be, in the models that we represent, fairly conservative or consensus-based in what we will show. And alternates are possible.
Excellent. Well, it was all very clarifying. Thank you so much.
Okay, looks like we need more talks on Neoproterozoic stuff to see if we live in desert world. Okay, Colin, looks like you convinced everyone to send you a note to model their favorite time interval. Thanks for your talk. And just a reminder that next talk will be from China, and potentially it will be in different time, possibly 4 p.m., but we will. So watch on announcement. So thanks everyone, and see you next week. Bye.
Thank you for listening, everyone.
Thanks. Thanks, Colin, again. Bye.
My pleasure.
Mhm.